Suppose I have an object moving along a straight line and I take a sample reading of its velocity each second. I'm going to make a little table of those readings that I make. In the first column I'll put the time t, and I'll record for each of the first 5 seconds what its velocity v of t is in meters per second. Suppose at t equal to 0 I read the velocity of the object and I discover that it's at rest, that its velocity is 0 meters per second. Then at t equal to 1 second, 1 second later I take a reading and I sample its velocity to be 3 meters per second. And I continue on. After 2 seconds I read its velocity to be 4 meters per second. At 3 seconds the velocity becomes negative, which means we are going to be moving in the reverse direction at 1 meter per second. And then it continues on with a negative velocity, so we're still moving backwards at minus 2 meters per second. And then at t equal to 5, the velocity is 0, meaning that the object comes back to rest and is stationary. I could summarize the information that I've given in the table with a plot of the velocity. Here I'm putting the time t on the horizontal axis, and I'm putting velocity v of t on the vertical axis. At t equal to 0, the velocity is 0 meters per second, so I've plotted that sample value there. At t equal to 1, the velocity is 2 meters per second, or I'm sorry, 3 meters per second. I've plotted it there, and then I've plotted the other points that appear in the table up to t equal to 5 seconds. What I'd like to do using the table is to estimate the distance that the object travels during the first 2 seconds. So between t equal to 0 and t equal to 2, I would like to use this information to predict how far I think the object would have traveled. To do that, I might use these sample values to make little estimates of the distance that it does over each little 1 second interval. So for instance, in the first second, the object is traveling 3 meters per second. I might as well assume that for that first 1 second interval of time that it's traveling at a constant value of 3 meters per second. It's not. Initially it's at rest, but I may just assume that it's constant for that first second. And then I would multiply the 3 meters per second times that change in time, that 1 second, to get a net change in position of 3 meters. 3 times 1 gives me 3 meters. Graphically, that change in position, that distance that's being traveled, is the area of that little rectangle that I've drawn here. In my calculation, I would record that first part of the estimate as 3 meters per second times 1 second, and then I would continue on to the next second of my journey between t equal to 1 and t equal to 2. At t equal to 2, it's traveling at 4 meters per second. I may as well assume for that second of the journey that it's at a constant 4 meters per second. And then I do the same calculation I just did. 4 meters per second times 1 second gives me 4 meters. And graphically, again, that's the area of that rectangle on that second. I would then add that expression into my estimate, 4 meters per second times 1 second, and add them together. And I can simplify this and I get 7 meters. So my prediction from reading the table or reading the graph is if I add up these two rectangular areas, I would expect to travel about 7 meters. Am I actually traveling 7 meters? Probably not. And remember, initially it's at rest and it probably took some time for the velocity to reach 3 meters per second. So it probably didn't travel as far as 3 meters. But anything could really happen in that first second, and we're not seeing a complete picture here. I'd like to continue this process on over to t equal to 5, but keep in mind that the velocity will start to become negative. So we'll start losing distance that we've traveled, and it would be really incorrect to call it the distance that we've traveled. I want to change the term I use here. What I'd like to do is estimate the displacement of the object from t equal to 0 to t equal to 5. This word displacement means the net change in position. I look at where I'm beginning and I'm going to look at where I end, and I want to figure out how far my net change in position was. I may cover the same ground twice, but I won't know that at the end of my calculation. At the very least, it should include these first two terms that we've already calculated, the 3 plus 4 meters that we travel, or at least estimate that we travel during the first 2 seconds. I'm now going to continue that process on and add some more terms in. At t equal to 3, I am traveling at minus 1 meter per second. I may as well assume that it's constantly minus 1 meters per second for that 1 second period, and then calculate my displacement, or at least estimate my displacement over that time period to be minus 1 meter. I am going backwards, I am losing a meter of distance, and therefore that will be taken out of my total. Graphically, it's the area of that region, of that rectangle there, but with a minus sign to indicate that we're losing distance. I then add that into my total, but again, it will ultimately be subtracted because of the negative velocity. At t equal to 4 now, I repeat that process. I'm traveling at minus 2 meters per second. We may as well assume that it's constantly minus 2 meters per second for that 1 second period. I multiply those together to get a displacement of negative 2 meters, which is the signed or the opposite of the area that I shaded in that rectangle. And I add that into my total, but again, it will be subtracting that quantity from the actual net result. Finally, at t equal to 5, my velocity is 0. I may as well assume that my velocity stays 0 meters per second for that 1 second period, and when I multiply 0 times 1, I would predict a displacement of 0 meters. I add that term in, 0 meters per second times 1, but of course that won't alter the final result at all. Finally, if I simplify all these expressions, 3 plus 4 minus 1 minus 2 plus 0, I'll get a net result of 4 meters per second. That's the displacement, or at least an estimate of the displacement from t equal to 0 to t equal to 5 seconds. Now, what we're calculating should be familiar to you. This kind of expression is what we called a Riemann sum when we were discussing definite integrals. What we're doing is we're summing up an expression. The terms that we're summing up are velocities being sampled at different time values. So I'm writing v of tk star to indicate these velocity measurements that are being taken at regular intervals. We then multiply by the change in time. In our case, it was these 1 second intervals of time that we're multiplying, the base of our rectangles, and then we sum them up from 1 to n. Continuing this process would give us an estimate of the displacement, and if we wish to improve that estimate, we would let the number of sample points that we're doing increase. In other words, we could let n go to infinity like we did with a definite integral to improve our estimates. We'll develop this idea more deeply in the next video, so continue on there.